Hi guys, today we are looking at the chapter Systems of Particles and Rotational Motion. Now, this is the 7th chapter of your physics syllabus in grade 11. Now, in order to complete this chapter in one video, we're using a mind map. So, let's begin. Now, this is the mind map that we're going to be using. As you can see, it covers all your basics for your school exams and to some extent for your NEET and JEE exams as well. Now this chapter is now divided into 10 portions, and these mind maps will be sectioned to give you convenience of so that you can read better. Okay. So this is the main tree that we're going to be looking at. So this is the chapter, Systems of Particles and Rotational Motion. Now this is a very important chapter in your physics syllabus because we have to look into the earlier chapters that you've studied, such as work energy power, laws of motion, and motion in a straight line, motion in a plane, etc. So all of the concepts that you studied there are applied here, and also we'll be looking at two new concepts. So those are the ones which are outlined in the chapter. So the first part of the heading is systems of particles. Now this refers to an extended body. An extended body will have more than one particle. Now, for example, we can give your pencil or a pen or your smartphone, etc. Those are objects which have more than one particle. Now, the reason why we are looking at systems of particles in this chapter is that in your earlier chapters, we have dealt with point objects. So the motion of point objects was dealt in the previous chapters, such as laws of motion, motion in a straight line, etc. Now in this chapter, we will be looking at motion of an extended body. And to help us in identifying motion in an extended body, we will be learning about center of mass, position of center of mass, velocity of center of mass, acceleration of center of mass. And then we will be moving on to rigid bodies and radius of gyration, which will complete the motion of an extended body or system of particles. Now, the next part of this chapter is rotational motion. So, in our earlier lessons, what we did was we looked at motion along the three Cartesian axes, the x-axis, the y-axis, and the z-axis. So, these motions will have all of the particles of the object move with the same velocity. But in rotational motion, what we do is we put the center of mass in, which is stationary, and then we move the object around it. So the object or the system of objects will have a stationary center of mass, and it will have angular velocity, angular displacement, etc. So we will be learning about inertia, torque, angular momentum, and then some equations of rotational motion. So these are the things that we'll be covering in this mind map. So they are the essential parts of systems of particles and rotational motion. These are pretty important for your exams. So let's begin. So now we move from the introduction of systems of particles and rotational motion to center of mass. That's marked as number 2 in this mind map. Now let me go to the extended image. Now, center of mass. What do you call as something as a center of mass? So the center of mass is defined as the point where the whole mass of the system is supposed to be concentrated. So in order to make motion of an extended object easier, we consider a point in the object where it's supposedly all of the mass of that point is concentrated. So that one point will have the mass of the whole extended object. So that is known as center of mass. Now, in center of mass, we'll be studying its position, how to calculate the position of center of mass. And then we'll calculate velocity of center of mass and acceleration as well. So let's move to position of center of mass, which is marked as number 3 in this mind map. Okay, from 2 to 3. Now, in order to calculate the position of center of mass, we use the formula RCM is equal to sigma I is equal to 1 to n MIRI divided by sigma I is equal to 1 to n MI. Now, to make this matter simple, suppose you have one object moving, we need to find the position of its center of mass. So what we do is we multiply its mass by its length and divide it by the mass. So that gives you the position of center of mass. And suppose if we have two bodies in a system, to find the center of mass of the system, we will do the following formula. M1 R1 plus M2 R2 divided by M1 plus M2. Now for more objects such as 3 or 4 object systems, we will add all of them. So in order to give a general formula, we use this summation formula, that is sigma I is equal to 1 to n, mi, m is for mass, r is for the length or the distance, and divided by sigma I is equal to 1 to n mi, and again m is the mass. Now, when you're calculating the position of center of mass of the system, we need to look at a couple of points which are pretty important. The first point here says that the position of center of mass of an object changes in translatory motion but remains unchanged in rotatory motion. Now, if you're moving an extended object along the x-axis or the y-axis or the z-axis, the center of mass and all the other particles of the body will be moving in the same velocity. However, in rotatory motion, the center of mass will be fixed, and the whole system or the object will be rotating around the center of mass. So that's the first point. The second thing that you need to keep in mind is that the position of center of mass depends upon the shape, the size, and the distribution of mass of the body. Now, when you have a regular shaped bodies such as circles, discs, rings, etc., the center of mass of the object will be in its geometrical center. And for irregular shaped bodies, the center of mass does differ. Now, the distribution of mass is now, in order to make this phrase simpler, we will imagine an arrowhead. An arrowhead is the shape that you find on the head of an arrow. And in this case, the unique thing is that the center of mass is outside the shape. So the center of mass might be dependent on the distribution of mass. So it's near to the area where there is the more concentration of mass, but it does not need to be inside the shape. It can be outside the shape or in a place where there is no mass. For example, in a ring, the mass is in the exterior, but the center of mass will still be in the center, the geometrical center, which does not have any mass. So these are the 2 points that you need to keep in mind. So after this, we'll move on to acceleration and velocity of center of mass. So from here, we will jump over to 4, which deals with velocity of center of mass of the system and acceleration of center of mass of the system. Now, if you were thorough with the earlier formula, that is the position of center of mass of the system, that formula, if you memorize that formula, these 2 formulae are very easy. Now, instead of R, which is position, we multiply the mass of the object with its velocity. So that will give you velocity of center of mass. So the formula will be sigma I is equal to 1 to n. So n be any integer, any whole number, and mi is mass of the body, vi is velocity of the body, divided by the sum of mass of the bodies. So that will give you the velocity of the center of mass of the system. So if you have 2 objects, it will be m1 v1 plus m2 v2 divided by m1 plus m2. Similarly, for acceleration, we will remove velocity and put acceleration in its place. So if we multiply the mass of the body by its acceleration and then divide it by mass, you will get acceleration of center of mass of the system. So if you have two bodies, it will be m1 a1. So mass of the first body times the acceleration of the first body plus mass of the second body times the acceleration of the second body divided by the sum of the two masses. So that gives you acceleration of center of mass of the system. Now what's interesting is that velocity can be given as dr by dt, where r is position. So the derivative of position with respect to x gives you velocity. No, with respect to time actually. So when x is equal to t, dr by dt gives you velocity. And similarly, if you do the derivative of velocity with time, you get the acceleration of the body. So in that way, we can also relate the three formulae for position, velocity, and acceleration of center of mass of the system. Okay, so now we will move on to a new section. So in this section, we'll be looking at center of mass for rigid bodies, and radius of gyration. It's marked as number 5. Now, center of mass for rigid bodies. Now, the important point that you need to consider for center of mass for rigid bodies is that the center of mass for a rigid body, for instance, a sphere or a cylinder, the center of mass of those bodies will be independent of the state of rest or of motion of the body. So whether a cylinder is moving or it's at rest, the center of mass of that body does not change. Now, all this talk about rigid bodies will keep you wondering, what is a rigid body? Well, as you can see here, a rigid body is a body with perfectly definite and unchanging shape. So a rigid body undergoes inelastic collision. Hark back to work energy and power. So if you collide your pen against a wall, the pen does not deform the way a rubber ball does. So in that case, the pen becomes a rigid body. So that's all you need to know about rigid bodies. A body that does not change its dimensions, such as volume, shape, etc. And it undergoes inelastic collision in work energy and power. Now, the next topic that we're going to tackle is radius of gyration. Now we know that the center of mass of a system is the center at which the particles of the system rotates. Now to find out the radius at which these particles rotate, we use a quantity called radius of gyration. Now it's represented by k. Now the first formula states that k is the square root of the sum of squares of position of n particles divided by the number of particles. Now if you have two particles A and B, with the position of A is R1 and the position of A is R2 from the center of mass, we will write the radius of gyration as the square of the position of the first object plus the square of the position of the second object divided by 2 and then put it under a square root. So that gives you the radius of gyration. Now, alternatively, we can also calculate the radius of gyration in another method. The second formula here states that k is equal to the whole root of I divided by m. Now, this states that I refers to inertia, which is the rotational analog for mass, and m here represents mass. So if you divide the inertia of a body divided by the mass of the body and then do a square root of the value, you will get the radius of gyration. So both these formulae will give you the same value, k, which is the radius of gyration. Now with the radius of gyration, we will be completing our section called system of particles, which is regarding the motion of an extended body. Now we move on to the sixth part here. Now, inertia. Now, in the previous section, we said that inertia is the rotational analog of mass. How do you calculate the inertia of a body? Inertia here in this formula says that inertia is the sum of I is equal to 1 to n. So, n particles. Mi or I square. So, if you have one object and you need to find out its inertia while it's rotating, you say that the inertia of the object is the mass of the object times the square of its dimensions, such as length, area, etc. Now, if you have two objects, r will be the distance between the two objects, the displacement. So inertia in general is mass times r, or position, or length, or radius, etc. So when you're calculating inertia, it is m into r. And when you have more than one object, we do m1 r1 plus m2 r2 plus etc. till mn rn, which is given in this summation formula. Now, in the section of moment of inertia, we will be learning about the theorems of moment of inertia. Now, there are two theorems of moment of inertia. They are parallel axis theorem and perpendicular axis theorem. Now, once we look at these theorems, we will be moving on into some regular shaped bodies, and we will learn the formulae for their moments of inertia. Okay, so let's move on to the seventh part of this mind map. So the sixth part has been inertia. Now we move on to the seventh part, which is both these theorems. Now here we go. Theorems of moment of inertia. Now, as you know that there are two theorems for moment of inertia. The theorem of parallel axis and the theorem of perpendicular axis. Let's move to the theorem of parallel axis. Now, the statement for the theorem of parallel axis is that I is equal to ICM plus MR square. Now, I here stands for inertia. ICM stands for moment of inertia about the center of mass. And M is for mass and R is for the distance. So if we need to find out the moment of inertia of an object about an axis which is parallel to the moment of inertia about the axis passing through the center of mass, what we do is we add the value of the moment of inertia about the axis passing through center of mass, ICM, and we by the product of the mass of the object times the square of the distance between the two axes. So this gives you parallel axis theorem. Now here ICM is said as moment of inertia about the parallel axis through the center of mass. Now when you have to find out the moment of inertia about an axis which is parallel to the axis passing through the center of mass, we use this formula for the theorem of parallel axis. Now, we move on to the theorem of perpendicular axes. The statement here states that Iz is equal to Ix plus Iy. Now, Z, X, and Y are the three Cartesian axes, the x-axis, the y-axis, and the z-axis respectively. Now, here Ix, Iy, and Iz are moments of inertia about perpendicular axes x, y, and z respectively. So it's in a Cartesian figure. So what this formula says is that to find the moment of inertia of an object about the z-axis, we add the moments of inertia about the other perpendicular axes, namely x and y axis respectively. So these two formulae are important in the sense that when you need to calculate the moment of inertia of certain regular bodies or irregular bodies, and you need to find them in a specific axis, and that axis may not be the axis passing through the center of mass. So in that case, we use the parallel axis theorem and the perpendicular axis theorem depending on the situation. So that completes the theorems of moment of inertia. Now we move on to the eighth part of this mind map. Now this shows some formulae for regular shaped bodies. Now let me expand this picture. Now the heading here is moment of inertia of some regular shaped bodies. Now for grade 11 school exams, we usually ask, the questions are usually from a rod, a ring, a disc, and a solid sphere. Now if you want to study more objects such as hollow sphere, etc., you can do so. But for your school exams, these four figures are sufficient. Now, when you go for the case of a rod is a one-dimensional object. So we consider a rod as a one-dimensional object, and the first formula gives you the moment of inertia about the axis passing through the center of mass. Now, in here it's given ml square by 12. M stands for the mass of the body, L stands for the length of the rod. So we square the length of the rod and multiply it with the mass, and then we divide the whole value by 12 to get the moment of inertia about an axis passing through the center of mass and perpendicular to the rod. Now, if we want to find the moment of inertia of the rod about an axis passing through an edge, we use the formula ml square divided by 3. Again, m stands for mass, L stands for the length of the rod. Now, the formula ml square by 3 was derived from the earlier formula ml square by 12 using the parallel axis theorem. Okay, so this shows you the reason why we need to study the parallel and perpendicular axis theorems. Now let's move on to the second figure, which is a ring. A ring has mass distributed about its perimeter, but has no mass between the center and the perimeter. So essentially, it is a string of mass about the perimeter and no mass in between. Now this shows you the thing that we asked, the second point that was present in the third part, which says that position of center of mass depends upon distribution of mass. So let's move on. Now for a ring, the moment of inertia of an axis passing through the center of mass, which is perpendicular to the ring, will be represented as mr square. Now in this case, m is the mass of the ring, the mass that's present in the perimeter, and r square will be the square of the radius of the ring. Okay, so if you have a ring and you have an axis which is passing through the center of mass of the ring, and it's perpendicular to the ring, the plane of the ring that is present, and you need to find its moment of inertia, you use the formula mr square. Now the second formula is for the moment of inertia of a ring about an axis which is passing through its diameter. So it's in the same plane as the ring, and it's a diameter. So it means that it passes through the center of mass, and while it's passing through, it passes through the largest chord, which is the diameter. Now this formula, which is mr square divided by 2, is derived from the earlier formula using the perpendicular axis theorem. Now mr square by 12, where m is the mass of the object and r square is the square of the radius of the ring, gives you the moment of inertia of a ring about an axis passing through its diameter. Now from a ring, we will move on to the third figure, which is a disc. Now in a disc, the mass will be distributed throughout the whole area. So the moment of inertia about an axis passing through the center of mass of a disc will be given by the formula mr square divided by 2. Again, m stands for mass of the disc and r square is the square of the radius of the disc. The second formula, as in the case of the ring, will be the moment of inertia about an axis passing through the diameter of a disk. Now this, again, by using perpendicular axis theorem, we get the formula mr square divided by 4. Now m is the mass of the disk and r square is the square of the radius of the disk. The final figure in this mind map is a solid sphere. Now in most questions, we will be asked to find the moment of inertia of a solid sphere about an axis passing through its diameter. Now a solid sphere is a 3D figure. So any axis would still be the moment of inertia, would still be the axis passing through its diameter. Now this formula, 2 by 5 mr square, gives you the moment of inertia about that axis. Now m here stands for the mass of the solid sphere and r square is the square of the radius of the solid sphere. Now with that, we complete moment of inertia. And next, we will move on to some equations of rotational motion. So from one end of the mind map, we now fly to the other end. Now let me enlarge this image for you. Now the heading here is equations of rotational motion. Now, in your third chapter in physics, that is motion in a straight line, we've studied 3 formulae. V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. Well, these 3 formulae are exactly the same. The only difference here is that we use rotational analogs for the quantities that we have described in the earlier formulae. Okay, so omega in rotational motion is the same as v or velocity in in translational motion. So omega is referred to as angular velocity. Now here omega 2 and omega 1 would refer to v, that is final velocity, and u, that is initial velocity, respectively. Now the third thing here is alpha. Alpha refers to angular acceleration, and again, angular acceleration is the same as linear acceleration in translational motion. Now, in order to find angular acceleration from linear acceleration, we multiply it by r, that is the distance. So since an object is undergoing rotational motion, we find the radius, we find the linear acceleration, and then we multiply them together to get the angular acceleration. Similar with velocity. So you need to find angular velocity. Omega will be rv. No, wait. V is actually equal to r omega. This you have studied in motion in a plane. So the actual formula is V is equal to r omega and acceleration is equal to r alpha. So we multiply the radius and the rotational analog to get the translational analog. Okay. So the next figure, the quantity here is theta. Theta is the rotational analog for distance. So theta is angular displacement while s is linear displacement. Now omega naught again refers to initial velocity u. T in both cases stands for time. And again alpha stands for angular acceleration. So the first formula will be omega 2 is equal to omega 1 plus alpha t, the same as v is equal to u plus at. And the second formula is theta is equal to omega naught t plus half alpha t square, which is s is equal to ut plus half ad square. The third formula here is omega 2 square is equal to omega 1 square plus 2 alpha theta. So that will be the same as v square is equal to u square plus 2as in motion in a plane. Motion in a straight line actually. So in motion in a straight line, we have studied these 3 formulae. Now we revisit these formulae, but with the rotational analogs. Okay, so these are important stuff that you need to keep in mind, especially for problems. So let's move on to the last part of the mind map. So this deals with torque and angular momentum. Now, torque is also known as couple or moment of force. So it basically is the rotational analog of force. And in order to find torque, we use the following formulae. Now here, tau bar, which is the vector for torque, is given as the cross product of r bar, which is the position vector, and f bar, which is the vector of force. So this r bar cross f bar is a cross product, and in a cross product, we usually get the magnitudes of the two values and then multiply it by sine theta as well. So we multiply the radius, we multiply the force, and then we multiply sine theta to that to get the cross product of position and force. So torque will be the same as Rf sine theta, which is the same as R bar cross F bar. Now rotational torque can also be thought of in rotational analogs as I into alpha. Now here I stands for inertia, which is the same as mass, and alpha stands for angular acceleration, which is the same as linear acceleration. So torque is equal to inertia into angular acceleration would be the same as F is equal to m into a, mass into acceleration, the stuff that you find in laws of motion. Okay, so that's all you need to know about torque. So this is the main thing that you'll be asked in your questions. So you'll be given some torque and you need to find inertia or angular acceleration. Or it could be the other way around. You'll be given angular acceleration and inertia and you need to find torque. Or it could be part of a bigger problem. Now the final subtopic of this chapter, that is system of particles and rotational motion, is angular momentum. Now angular momentum is represented by L. Now linear momentum, if you remember, motion in a plane was represented by P. In motion in a plane and laws of motion, we represent linear momentum by P. So angular momentum here is represented by the following formulae. Now the first is the rotational analog of the formula that you have studied earlier. This is I into omega. I is inertia, which stands for mass, and omega is angular acceleration, which is just the same as linear velocity. Omega is angular velocity, I'm sorry. This is angular velocity, and L is equal to I omega would be the same as P is equal to mv. So this will let you understand the similarities between mass and inertia, as well as the similarity between linear velocity and angular velocity. Now, angular momentum would be the same. For all these formulae. Now we need to look at the second formula. The second formula of angular momentum is, it states that angular momentum is the product of the mass of the body times the velocity of the body times the radius. So m and v are translational quantities. So mass is in translational motion and velocity is also in translational motion. So we multiply these by the radius since it's a rotational motion. Now we separate r from the other two and write it as r and with the multiplication symbol, and we write mv. We can combine mv to linear momentum. So that's what's represented in the next formula. Angular momentum is equal to r into p, which is radius into linear momentum. Again, this is a cross product. So therefore, you will be getting a sine theta at the end of the last formula. So this is the magnitude of the radius, the magnitude of the momentum, and then you get a sine theta. So angular momentum would be radius times linear momentum times sine theta. Okay. So that ends the chapter Systems of Particles and Rotational Motion. We hope you found this mind map interesting, and I hope that you understood all of the basic concept that you need to apply in the problems for systems of particles and rotational motion. This surely would help you in your school exams and to a certain extent for your needs and JEE exams. Okay, so this video is going to be ended here. Please subscribe to our channel, Brainlets Audios, for receiving more educational videos, stories, etc. Please subscribe to our channel and please like this video for getting more useful content. And don't forget to give us your comments in the comment section below. We'll be happy to improve upon anything that we might have missed out. So until next time, bye bye.